In this video, we will watch and understand what is a Scada system. Scada is a control system architecture. It comprises computer, network data communication, graphical user interface for high-level process supervisory management, while also comprising other peripheral devices like programmable logic controller and PID, functional integral derivative controllers, to interface with process plant or machinery. Scada consists of 5 main components. First is field instrumentation, that are sensors and data collecting devices. And second is field controller, that is RTU, remote terminal units, and PLC, programmable logic controllers. Third is HMI, that is human machine interface. And fourth is network connectivity, that is field buses and protocols. And fifth is database or historians, which is used to store the data in clouds. So let's understand what are the other perspectives on Scada.
Supervisory control and data acquisition, or Scada, is an automation control system that is used in industries such as energy, oil and gas, water, power, and many more. The system has a centralized system that monitors and controls entire sites, ranging from an industrial plant to a complex of plants across the country. A Scada system works by operating with signals that communicate via channels to provide the user with remote controls of any equipment in a given system. There are 5 essential composing parts of a Scada system: human-machine interface, or HMI, supervisory system, remote terminal units, or RTUs, programmable logic controllers, or PLCs, and communication infrastructures. The HMI processes data and sends it to a human operator, where they can monitor or control the system. The supervisory system gathers the data and sends commands or operations to the process. The RTUs connect sensors and convert their signals to digital data and send it to the supervisory system, where it can be stored in a distributed database. PLCs are used as field devices because they are much more versatile and economical than process-specific RTUs. Finally, the communication infrastructure delivers connectivity to the supervisory system and then to the RTUs and PLCs for the user to command. The communication infrastructure is necessary to relay data from remote RTUs and PLCs, which run along electric grids, water supplies, and pipelines. Communication is the absolute most essential link for a Scada system to operate properly. However, how well the system manages communication from HMI to RTUs and PLCs fundamentally determines how successful a Scada system can be. Scada systems are crucial for industrial organizations since they help maintain efficiency, process data for smarter decisions, and communicate system issues to help mitigate downtime.
Now we will understand what are the applications and uses of Scada. So, the Scada is most probably used in industrial process like manufacturing, process control, power generation, fabrication, and refining, and in infrastructure, water treatment and distribution, wastewater collection and treatment, electric power transmission and distribution, wind farms distribution, and in facility process like buildings, airports, ships, space stations. These are the various applications of Scada. Do you know that there is a belief in Scada network that they are secure because they are disconnected from the internet, and also because of the use of the specialized protocols and proprietary interfaces. But this is not a true fact, because in June 2010, antivirus security company VirusBlokAda reported the first detection of malware that attacks Scada system, that is Siemens WinCC or PCS7 system running on Windows operating system. The malware is called stagnant, and it uses 40 days attack to install a rootkit, which in turn logs into the Scada database and steals design and control files. In October 2013, National Geographic released a documentary titled American Blackout, which deals with an imagined large-scale cyber attack on Scada and the United States electrical grid. So, we cannot say that Scada system is totally secure.
A Scada system is a collection of both software and hardware components that allows supervision and control of plants, both locally and remotely. The Scada also examines, collects, and processes data in real time. Human-Machine Interface, or HMI software, facilitates interaction with field devices such as pumps, valves, motors, sensors, etc. Also within the Scada software is the ability to log data for historical purposes. The structural design of the standard Scada system starts with remote terminal units, or RTUs, and/or programmable logic controllers, or PLCs. As you know, RTUs and PLCs are microprocessors that communicate and interact with field devices such as valves, pumps, and HMIs. That communication data is routed from the processors to the Scada computers, where the software interprets and displays the data, allowing for operators to analyze and react to system events. Before Scada, plant personnel had to monitor and control industrial processes via selector switches, push buttons, and dials for analog signals. This meant that plants had to maintain personnel on site during production in order to control the processes. As manufacturing grew and sites became more remote in nature, relays and timers were used to assist in the supervision and control of processes. With these devices employed, fewer plant personnel were required to be on site in order to oversee and control operations. While relays and timers did provide some level of automation, the panels required for these devices took up valuable real estate. Troubleshooting was a nightmare, and reconfiguring was difficult at best. These issues, in conjunction with the need to grow even larger industrial plants, helped to facilitate the birth of automation. As you may know from previous videos, controlling industrial plants via processors became a reality in the 1950s. Gas and oil, utilities, and manufacturing were major users of these new technologies and supervisory control. About a decade later, telemetry came on the scene to offer even more remote capabilities, with automated communication and data transmission to remote monitoring locations. Another decade later, the term Scada was used to describe systems with PLCs and microprocessors that were being used for the monitoring and control of automated processes on an even greater scale than ever before. Scada, back then, was anything but practical. They were colossal machines, mainframes really, and since networking was not yet in the picture, they were standalone units. In the next couple of decades, the 80s and 90s, with computer systems getting smaller, the advent of local area networking or LAN, and HMI software, Scada systems were able to connect to related systems. Unfortunately though, the communications were typically proprietary, which meant that connections outside of the particular vendor of the Scada system were not allowed. This early Scada was coined Distributed Scada Systems. Later in the 90s and 2000s, Scada began to implement open system architectures, with communication protocols that were not vendor-specific. As you can imagine, this opened up Scada's ability to connect with varying vendors. This newer, more improved Scada was then called a network Scada system. Newer and improved Scada unfortunately didn't last long. With computer technology growing rapidly, IT development quickly gathered steam. The default database for IT became Structured Query Language, or SQL databases. Scada developers didn't implement these standard databases, so Scada became out of date rather quickly when other technologies so rapidly changed. Current-day Scada systems have adapted to the changing technologies and have a great advantage over the older Scada systems. With the adoption of modern IT standards such as SQL and web-based applications, today's Scada allows for real-time plant information to be accessed from anywhere around the world. Having this data at the operator's fingertips facilitates improved plant operations, allowing for responses to Scada system cues based on field-collected data and system analysis. These operator interactions can be from a computer right on the plant floor to an office building in some other region in the world. Advancing technologies have indeed made the world seem like a very small place, relatively speaking. And because the current Scada system software has typically adopted the SQL database model, historical collection of data may be logged and used in trending applications to further improve plant processes, as well as creating mandated record keeping for some of the industries out there. Essentially, Scada is a collection of hardware and software components. This collection of components begins with real-time data collected from plant floor devices, such as pumps, valves, and transmitters. These components don't have to be from a particular vendor. They just need to have a communication protocol that the processor can utilize. Data collected from the field devices is then passed to the processors, such as PLCs. From the processor, the data is distributed to a system of network devices. These devices may be HMIs, end-user computers, and servers. On the HMI and end-user computer, graphical representations of the operations exist for operator interactions, such as running pumps and opening valves. This data may also be analyzed and used to enhance plant production and troubleshoot problems.
A RTU is a microprocessor control electronic device that is used to interface objects in a physical world to a Scada system by transmitting telemetry data to a master system and by using messages from the master supervisory system to control connected objects. An RTU comprises of communication interface, microprocessor, non-volatile memory, environmental sensors, override sensor, and bus for interfacing.
Do you want to benefit from the advantages of an integrated engineering environment for control, drive technology, and process visualization? Do large amounts of data need to be configured in an extremely short time? Thematic WinCC version 7, you have at your disposal a scalable and open Scada system for maximum plant transparency and productivity. Through web-based access, you have your plant in view at all times and wherever you are. But are you sure that everything is running smoothly? You can only find this out by consistent analysis of quality or energy data. You will be amazed by how much optimization potential you discover. Use this information as a key to efficient production. Do you need a vendor and platform independent system that enables scalable solutions for use on different hardware systems? Do you want unrestricted worldwide access to your plant via web and iOS or Android apps? With Thematic WinCC Open Architecture, you use all these options in one system.
It is energy self-sufficient by using a battery, an accumulator with solar panel, or a combination of both. The RTU offers 8 digital and 4 analog inputs, as well as 4 digital switch outputs. Different sensors for measuring the pressure, flow rate, water level, filling levels, temperature, etc. can be connected to the analog inputs, and the RTU serves as a power supply for the measurement. For optimizing the energy consumption, the RTU 3030C is mostly in the so-called sleep mode and only switches to update and communications mode due to time or event control for the measurement, secured transfer, and if needed, logging of the measurement values. When configurable threshold values are exceeded, the RTU can warn the service staff. A web-based management allows for easily setting all necessary parameters for the sensors, update times, communication parameters, etc. All measurement values are assigned a timestamp, are buffered in the RTU, if needed, and transferred to the control center via the integrated UMTS modem. The RTU 3030C supports the different telecontrol protocols, Telecontrol Basic, DNP3, and IEC 60870-5-104. A robust design of Thematic RTU 3030C allows for the use under harsh conditions, ranging from temperatures of -40 centigrade to 70 centigrade. That means it can be flexibly used in various applications, such as water and waste management, agriculture, or stock.
The Lucy switchgear Scada system is designed to safely and reliably monitor and control the operation of large electrical networks. The system collects and processes data sent from other substations, providing the operator with a comprehensive view of the whole network. This typical example shows a SCADA-monitored electrical network providing electricity from a primary substation to a range of regional consumers. The primary substation provides a feed-out to a residential area, a commercial city district, and the local airport via other local substations. A busy port and a small rural community are also supplied by the primary substation through another circuit. Let's see how the Scada system is used to manage and maintain the network during a fault. On a remote rural section of the network, a fallen branch causes damage to the overhead power lines feeding substation 2. This break in supply causes the circuit breaker for this line to trip at the primary substation, leading to a total power outage to both the port and the rural community that rely on this circuit. Power to the rest of the network remains unaffected. The Scada system receives notification of the circuit breaker trip, then uses the fault passage indicators positioned around the network to determine where the fault has occurred. In this case, the fault passage indicator at substation 2 has not tripped, so at the remote Scada data center, the operator is informed that the fault must be somewhere on the line between the primary substation and substation number 2. The operator can now use the Lucy switchgear Scada system to isolate this area and reroute power to customers without a supply. The operator remotely opens the incoming switch from the primary substation to substation 2. And then opens the outgoing switch from substation 2 to the rural community. This totally isolates the fault area from the rest of the network. The operator can now close the outgoing switch at substation 3 to re-energize the link to substation 2. Substation 2 can now reinstate the supply to the port. In order to avoid overloading one side of the network, the operator chooses instead to close the GX switch on the backfeed to the rural community to reinstate their supply. Supplies to all affected areas are now complete and the faulty line is safely isolated from the network, allowing the operator to arrange for a repair. Typically, the network will be sectionalized and power rerouted within 3 minutes of the original fault. Scada enables the operator to direct the repair team to the specific area of the network at which a fault has occurred. Once the operator has confirmation that the repair is complete and all maintenance crews are clear of the area, Scada can be used to restore the system to its usual operation. The newly repaired line is tested first by closing the primary substation's outgoing switch to substation 2. The line energizes as normal, confirming the repair. The operator can now close the incoming switch to substation 2, reinstating the original supply route. The backfeed from substation 3 is no longer required, and so the Scada operator can open its outgoing switch. With the load removed from the lower side of the network, the rural community outgoing switch from substation 2 is closed, creating a parallel circuit for the area. The final step for the Scada operator is to reopen the GX switch to disable the backfeed to the rural community, restoring the standard operation of the whole network. The Lucy Scada system works in conjunction with our complete range of switching and protection solutions to provide operators with unprecedented control and management of their networks.
The Gotthard Base Tunnel is a mammoth project. At 57 kilometers, it's the world's longest railroad tunnel. The tunnel's purpose is to ease the burden of increasing freight traffic on Switzerland's sensitive alpine ecosystem. Passenger trains will also be able to pass through the tunnel at speeds of up to 250 kilometers per hour. Eventually, more than 200 trains a day will pass through the tunnel at speeds of up to 250 kilometers per hour. Because the trains will operate beneath as much as 2,300 meters of solid rock and with up to 28 kilometers to the nearest tunnel exit, safety is extremely important. If a train is unable to reach the tunnel exit due to a defect, it will head for one of the 2 emergency stop stations in the interior of the mountain. For From there, up to 1,000 people can be evacuated and can transfer to a relief train in the other tube. To prevent the occurrence of an emergency, the tunnel system is equipped with countless sensors, monitoring facilities and controls. These are connected to 2 tunnel control centers at the north and south portals via thousands of kilometers of cable. Siemens has installed a tunnel control system, the heart of the monitoring system, at each of the 2 centers. The complete system, including the tunnel control system, has now undergone 6 months of intensive testing over a fully equipped 17-kilometer stretch.